Welcome to all. My name is Cardoen. I'm the technical lead process automation at AG Solution. This presentation has the goal to enlighten the audience about the digital twin we're building for a market-leading organization in the food and beverage industry. After a short introduction, I'll explain you how the digital twin fits for process simulation and I/O validation. A conclusion will be stated, and after the presentation, there will be time for questions and answers. The concept of a digital twin was first pioneered during the rescue mission of Apollo 13 in the 1970s. The digital twin model allowed engineers to test possible solutions from ground level. The concept was further developed at the University of Michigan in 2003 and was later called digital twin by NASA in 2010. Every digital twin consists of three parts: a physical part, a digital or virtual part, and a connection layer. Please keep the last sentence in mind. The context in which we developed the digital twin was that of a migration project within the food and beverage industry. AG Solution is executing a software migration project where an obsolete DCS is being replaced by a more modern and future-ready DCS. This is a distributed control system to monitor, to operate, and to control the process. Overall, the biggest impact will be the new operating system. In this story, the operator will need extensive training to get use of the new control philosophy. To make the switch to the new DCS, a limited time slot was foreseen, so it's critical to have the possibility to test the in and outputs up front, as this is typically a very time-consuming task. Another thing to keep in mind, this must be done without disturbing daily production. More specific, we created a digital twin to replicate a complex process where multiple food components are derived from wheat. The image represents a very simplified version of the process. In reality, the process has been designed on 100 pages of P&IDs. These are process and instrumentation diagrams, and thousands of in and outputs are being controlled by the process. So the reality is a complex environment. Typically, a project starts with writing a functional design specification, or FDS. This is describing in detail how the application software should work. Based on this FDS, the application software will be written. Once the software has been tested in-house, a quality check will be done by the customer during the factory acceptance test, or FAT. Developing the digital twin is done during the writing and the FAT project phases. The digital twin itself will be rolled out during the test phases. This to facilitate the testing and to optimize the digital twin to have it process-wise as close as possible to the reality. Once the application software has been accepted, operator training can start. Here again, the digital twin will find its use. After a period of site acceptance tests, or SAT, the new application software will be deployed. In and output testing are part of the SAT. Our digital twin will help in reducing the testing period. We've been using following Siemens tools. PCS7 is used to write the application software to monitor, to operate, and to control the process. SIMIT is the simulation framework that is used to build the digital twin. At your left, you see the buildup of the application software with PCS7. SIMIT at your right follows the same buildup. Every project consists of uses control module types from a master data library. In short, logic and blocks to monitor a value, to control a pump, to open and close a valve, and others. The SIMIT library will contain the corresponding equivalents. Control modules, the actual valves, the actual process values, are created with the types from the master data library. SIMIT modules will be based on the SIMIT templates. Application software will control equipment according to functional design. The process modeling, its SIMIT will respond or react to application software by providing the necessary process values. To come to a process simulation, following aspects need to be explained. The coupling will be the link, the connection layer between the real and the digital world. Said otherwise, this coupling with the I/O symbol table will be the main link between PCS7 and CIMIT. The CIMIT modules will ensure that the core functionality of equipment is guaranteed within the process simulation, like opening a valve, starting a motor. With this example, you see the interaction between the real and the digital world. The application software at your left controls the valve with the control module. If the valve opens, it should react in the field. So the software expects the response that the valve is open. That exactly will now be handled by the digital twin. The digital valve, its CIMIT, receives the open command via the CIMIT module. The valve will leave its closed position. After a time, the open position will be reached. This open position will be transferred back to the application software via the coupling. Thus, the application software receives the response that the valve is open. This screenshot gives you a simple impression how it looks in the engineering environment. A next step in the process simulation is the process modeling. The modeling will be based on the position of valves, on running of pumps, conveyors, etc. Taking that into account, the process values can be calculated. These calculations can go from simple to more complex. They can also require input of a process engineer. Following slide will illustrate how the position of valves influences the level process value. Here we have a rather simple process, an inlet valve with a filling flow meter, a tank with a level transmitter, an emptying valve with a corresponding outlet flow. The application software will open the inlet valve. The tank level will start increasing according to a certain filling rate. As long as the filling valve is open and the outlet valve remains closed, the level keeps on increasing. When both in and outlet valve are open, the level will now be depending on the filling rate and also depending on the emptying rate. Here we see that the emptying rate is slightly higher than the filling rate, so the level starts decreasing. When only the outlet valve is open, the level keeps on decreasing. This is a simple overview of what process modeling can do. This slide shows you the engineering environment. A process value is determined by a simple calculation. Via the CIMIT module and the coupling, the process value is sent to the application software where it can be processed. The simulation framework offers snapshot management. This is creating an as-is copy of a particular situation. From a stop state, the operator can train and optimize the startup. Fault scenarios can be introduced to train the operator in troubleshooting. Returning to a normal production state can be a matter of a click. No need to say snapshot and training go well together. The process simulation offers several operational advantages. It has proven to be a huge aid for the operator. He will have time to be trained and continue training himself in a live but digital environment. He will have time to familiarize himself with the new control philosophy and the new look and feel of the new operating system. All this will lead to a smoother startup. Typically, it can take easily a week and longer to perform the classical in and output testing. By means of the digital twin, the downtime related to this testing can be reduced. At first, the I/O symbol table will be tested with the existing software. When the behavior of in and outputs is as expected, we can state that the symbol table is validated. Next, the validated symbol table will be tested with the new application software. The same testing routine will be performed. The application software will be modified where necessary so that in the end, all in and outputs behave the same. As the behavior will be identical and the fact that nothing will be changed in the field, remember, this is a software migration, we can state that there is no need for extensive in and output testing. Thus, the downtime due to this testing will be highly reduced. What are now the results of using the digital twin? It led to a reduction of the downtime by 80%. Can be brought down to the two main reasons: in and output testing upfront and extensive operator training. The latter led to a faster and better product quality after startup. The operational team has now a digital twin available for further training optimization. It's equally available to investigate and test possible process optimizations. What were now the critical success factors? Having an up-to-date I/O symbol table, the coupling between the real and the digital world must be flawless, understanding the process, and seeing and discovering possibilities like creating drivers to control the third-party systems, which are frequently used within the food and beverage industry. This conclusion brings me to the end of the presentation. Thank you for listening. Of course, it's a real challenge to reduce a complex to a 10-minute presentation. But if you have questions about the project of your specific situation, please get in contact and I'll be happy to advise.